although I recorded this morning, so that should be okay. In theory, fingers crossed. Sorry I didn't post Friday's lesson or Thursday's, I don't know. Kind of fell apart at the end of last week, having a little bit of a, too busy mental breakdown kind of thing, but that's okay. Back on track now. I had a weekend to regroup and life is better now. Okay. So we now are on solubility, and we had just finished qualitative analysis last day. And so I'm going to give you for homework, page 20, number 1A and number 2A, because I presume some of you probably still want to be reviewing for your test on Wednesday. Am I correct? Yes? Okay, so this is not a lot. It's basically do a qualitative analysis for a couple of anions, do a qualitative analysis for a few cations. Yes? Okay. And other than that, your homework is just to study for your test. So we are now going to move on to section 3.2 on page 23. And if you were doing this on your own, I would have you watch Professor Dave, but since we are here together, we might as well just do it together. So solubility, we're going to give it a temporary definition. We're going to come up with a better definition in just a little bit, but it is the degree to which a solute will dissolve in solution. So how well does the solute dissolve? Or how much can the solute dissolve? Now, back in grade 11, we learned that some ionic compounds are water soluble. And if a compound is water soluble on our little chart, that meant that it would dissociate completely in water. Okay, and that is water soluble. We also learned that other ionic compounds were insoluble, which means they do not dissolve. In water. Or if we have the components of an insoluble compound, so for example, if we had AgNO3 and AgNO3 and NaCl, and we mix the two, we would get, and if we check our data booklet, we can see that if we combine our outside ions, we get AgCl. If we combine our inside ions, we get NaNO3. And if we check our data table, we can see that chloride and silver are low solubility. So that means that this one is going to be our solid, and that would be our insoluble compound. Okay, so for example, this could be AgCl. Cl solid. And most of last year, we were just kind of like, okay, when you have AgCl solid, if you were to throw it into water or you had it as a precipitate, it would just still be there as AgCl solid. Now, because you guys are AP, we actually talked a little bit that wasn't actually true. This is not the complete picture. And one of the reasons we know it's not the complete picture is we don't actually use the word insoluble. We use the words low solubility. Yes? So that has a little different meaning. What that means is that we have low solubility. It means even insoluble compounds will dissolve to a small degree. So a small amount is dissolved. So on your solubility table, you see low solubility. Now, the degree to which a substance dissolved can be communicated by the solubility product constant, which is known as the KSP. And if we're like, what is this product of which they speak? What are we multiplying? We are multiplying the ion concentrations, the dissolved ion concentrations. And that'll become more clear when we do an actual example of that, okay? So we've got this solubility product constant. It's got a K value. And if it has a K value, that tells us that it is a system at equilibrium. Okay, so our system is at equilibrium. So what we've really got is we really have, and if you notice up here, we've got our concentration. We've got 1, 2, 3, 4 ions dissolved. Okay. Now, simultaneously, you'll have both of these okay, where we have dissolving, which would give us, instead of 4 particles, it would give us 6 particles, yes? But we also have, at the same time, recrystallizing. And because those are both happening simultaneously, you will still have 1, 2, 3, 4, 1, 2, 3, 4 dissolved particles. Yeah? Because the rate of the forward reaction is the same as the rate of the reverse reaction. The rate of dissolving is the same as the rate of recrystallization. Yeah? And we can tell that we are at equilibrium because concentration remains the same. Okay, so our macroscopic property, concentration, which is a macroscopic property, is constant. And why is the concentration remaining the same? Because the rate of dissolving which is the forward rate, is the same as the rate of recrystallization, which is the reverse rate. All right, and here is our introduction to the solubility product constant, the KSP. And you'll notice that in the equation for this, the solid is on the left in the reactants. Okay, and the ions are on the right-hand side. This equation here, this is called the solubility equilibrium equation, which we are going to call the S.E.E. And it is the equation that is used anytime we're doing anything with KSP. S.E.E. Now, just like any other K, it's the concentration of the what over the what. Like any other KEQ, it is the concentration of the over the. Excellent. Okay. And here we go. And we have here for our AgCl, you can see we've got coefficients of 1 and 1. So the powers those are raised to are the 1 and the 1. So our KSP then is just KSP equals. And of course, do we include solids? No. So there is no solid. All right. So there we go. And by convention, we always write the solid on the left. Those are going to give us the values that we will see in our KSP table, which is on page 5 of your data booklet. These are all assuming that you've got the solid on the left, and they'll give you those values, okay? If you had the solid on the right, it would give you 1 over those values, but we never do that because that would be silly, because the point of having standards for things is so that everybody does it the same way so you don't get confused. Okay, so probably my guess is that they chose it because this way is easier math, yeah? Rather than doing 1 over silver and chloride, all right? So that is our KSP expression. And now we are going to do a little interlude, which is the solubility equilibrium equation, the S.E.E., versus the precipitation equation, which we're going to call the P.E. And I know we use P.E. for potential energy, but quite frankly, you're not going to be writing precipitation equation in explanations anyway. You are simply going to write the precipitation equation. So I think if we refer to this in context as the P.E., it should be okay. Yes? Okay. So the solubility equilibrium equation, RC, has the solid on the left. So when we're writing a solubility equilibrium, the solid goes on the left. And because this is what we're using for a K, and because it is an equilibrium, what kind of arrow do we use? Equilibrium arrow. Okay, so this is our S.E.E, solubility equilibrium equation. And this is used for KSP. Now, if we are going to write a precipitation reaction, if we're going to write like a double replacement reaction where we get a precipitate, the precipitate, is that a reactant or a product? It's a product. So we should be writing the precipitate as a product, yeah? So in a precipitation reaction, we're forming a precipitate. So the product is the precipitate. So here we have our solid on the right, and most of the time we're not really concerned at all about the equilibrium that it forms with a few little ions. We're just like, the vast majority of the ions come together and form a precipitate. Do we care that a little teeny tiny amount is still dissolving? Not usually. And if we do, we actually do that as a second step. We're like, I might have a precipitation occurring, right? Where we've got our one-way arrow here and our solid on the right. And then afterwards, we're like, and now what happens with this KSP and the solubility? Okay, but it would always happen sort of like as a second step. You would never have your equilibrium there. Okay, so there's our solid. Okay, so our precipitation equation has the solid on the right. So be sure, and it is always a one-way arrow. Because if we want the two-way arrow, we're going to be using KSP, and that's by standard the solid on the left. So be sure when you're writing the equation that you are always choosing the correct equation, which is going to include the correct direction, solid on the left or solid on the right, and using the correct arrow, equilibrium for the C, one-way arrow for the PE, precipitation equation. You will lose marks if you choose the wrong one. So we're going to spend a little bit of time just seeing if we can pick the correct equation. Okay, so let's take a look at this very first one. We're going to pick either the PE or the S.E.E, and then we're going to write the equation. First one says, write the net ionic equation that occurs when equal volumes of 0.2 molar BaCl and 0.2 molar NH4-2SO4 are mixed. Tell your neighbor, do you think that we should be writing a precipitation equation or a solubility equilibrium equation? Are we doing anything with the KSP here? Nope. So don't use the solubility equilibrium equation. We are looking at what happens when we mix two aqueous things together. What type of a reaction is this? Double replacement. So if we combine our outside ions, okay, that's going to be our Ba and our SO4. You would get BaSO4. If we combine our inside ions, that would give us NH4 and Cl. Do we get a precipitate, or do we get two precipitates, or do we get no precipitate? One precipitate. Which one is it? BaSO4. We know that this one is aqueous because why? NH4. Our ammonium salts are always soluble, whereas barium sulfate is low solubility. So that's going to be our solid. Could you write the net ionic equation that forms BaSO4 solid? Who will be reacting? Ba and SO4? One-way or two-way arrow? One-way arrow? What am I missing? Charges, 2 plus, 2 minus, anything else? States, aqueous, and aqueous. Okay, and we're done that one. Yes? Cool. All right, our next question, we want to know the molar solubility of PBI. Oh no, we're told the molar solubility of PBI2 is 1.52 times 10 to the minus 3, and we're asked to calculate the value of KSP. Do we want to use the solubility equilibrium equation or the precipitation? Solubility equilibrium equation. Okay, now I'm going to tell you something. This is the only new thing here, really. Molar solubility means how much dissolves. Another way of saying how much dissolves is saying concentration, yes? So if I say the molar solubility of PBI2 is 1.52 times 10 to the minus 3 molar, I could rewrite that as the concentration of PBI2 is how much? 1.52 times 10 to the negative 3 molar. Yay! Is good? Excellent. Now, let's write our S.E.E. for this thing. What would we write on the left for our solubility equilibrium equation? PBI2, because the solid always goes on the left. Oh, look. In C, solid goes on the left. Look, S for solid, S on the left. Things I've never thought of before. So good. So there's our solid. And what kind of arrow do we use? Equilibrium arrow. Who are our products? Pb2 plus 2I minus aqueous. Now, we have not yet learned how to do KSP calculations, but you spent a whole unit doing KEQ calculations, and you just spent a unit doing KA calculations, yes? Could you write the KSP for this equation? I bet you could. Give it a go. Write the KSP for this equation. KSP equals. I don't need numbers. I just need the expression. Check with your neighbor when you're done. How many people think they can see what concentrations they would throw in there? Think about that for a minute. What concentrations would you put in there? Have a chat with your neighbor about that. What concentrations do we have for the lead and the iodide? Give me a little wave if you think you know. Got 1, 2. If I told you the concentration of HCl was 1.5 molar, what is the concentration of H plus? 1.5 molar. And what is the concentration of Cl minus? 1.5 molar. Why is that? Because it's a strong acid and the stoichiometry is 1 to 1 to 1. Yes? Now, if I say my concentration of PbI2 is 1.52 times 10 to the negative 3 molar, do I really mean that there are little PbI2s holding hands together in the water floating around? No. So I'm going to put that in brackets, okay? Because that's just telling me how much dissolves. Yes? And if that's how much dissolves of the PbI2, what is the concentration of Pb? 1.52 times 10 to the minus 3, because this is 1 to 1. Yeah? And what would the concentration of I2 be? Or sorry, not I2, of I. What would the concentration of I be? Negative 3, which is 2 times 1.52 times 10 to the negative 3. Okay? That's how we got that number there. Because it's twice as much because we have a coefficient of 2. Every time one lead iodide dissolves, you get 2 iodide ions. And so then what you're going to do is you're going to take those numbers and you can chuck them in here. 1.52 times 10 to the negative 3 times 3.04 times 10 to the negative 3 squared. And we get 1.405. No, 1.4047. Times 10 to the negative 8. Is that what you guys got? Did I do my calculation right? Yeah, I did. Okay. What would that round to? $1.40 times 10 to the negative 8 is good? Yes. So you've already learned part of section 3.3, even though we haven't even started it. Yeah? Because it's all things that you already know. You know how to write a K value or a K expression, yes? You know how to find the concentration of ions based on the concentration of the thing that's dissolving. And the only thing that was new was being told that the molar solubility means the concentration of PbI2. So that was the new thing. And other than that, and the fact that our K is called KSP, you know how to do this already because you guys are geniuses. Geniuses, you. Okay. All right. Let's try another one. Ooh, titration. Super fun. A student titrates a 10 milliliter sample of well water with 11.97 milliliters of AgNO3 to precipitate the chloride ion in the well water. What is the concentration of chloride? Is this an S.E.E. type situation or is this a P.E. situation? Chat with your neighbor about that. Think about this. You did titrations last year. And last year, in theory, you knew nothing about equilibrium. Maybe I told you a little bit. Maybe you learned a little teeny bit. So what kind of equation are we going to use? The PE. And it says to precipitate. Oh, there's another clue that it's going to be the precipitation equation. Now, this one is a little tricky to write because we have a compound and we have an ion that it is reacting with. And that throws some people for a loop sometimes. But what do we know about nitrate salts? Nitrate salts are always soluble. If that is the case, what kind of an ion is nitrate in our reaction? It will be aqueous and it will be a spectator. So if ever you're given like a compound and an ion, chances are it'll just be easiest for you to write what version of equation? Net ionic, okay? I mean, you can write AgNO3 plus Cl, but it's mixing and matching and tends to confuse people, right? They tend to be like, oh, I don't know what to do. So just be like, okay, what's actually reacting? Well, the silver and the chloride are actually reacting. Who would be the reactants in this precipitation equation? Ag and Cl. So we would have Ag plus and Cl minus. What state are those? Aqueous. And what do we get? AgCl. And that would be solid. And did I write my arrow the correct arrow? Yes. Okay. Do you guys know how? Yes, sorry. Because what you got is you've got some well water. Okay, so this is water out of a well. Yeah? And that well water, the chloride probably originally came paired. Some of it came paired with sodium, some of it came paired with potassium, some of it came paired with magnesium, some with calcium. So we don't know what the cations are, which is why we just talk about the chloride. And maybe we're just like wanting to know what the chloride concentration is in that water because it's been in the ground. It's just got all sorts of dissolved minerals. And maybe we're just trying to figure out, what is the concentration of calcium? What's the concentration of chloride? So we're just finding one of them. Yeah. And because chloride reacts with silver in this way, it is an easy one to do a precipitation titration. Okay. So instead of an acid-base titration where the acid neutralizes the base, in this case, the silver reacts with the chloride and forms a precipitate. And we'll actually do a lab like this. Oh, so much fun. Okay. And expensive. So appreciate it. Only my AP students get to do this one because silver ions are expensive. Okay. Yeah, like hundreds of dollars expensive. But it's a cool procedure. So anyway, okay, so we got this. Do you guys know how to do a titration calculation? Okay, so let's take a look at what we know about the silver ion. What information are we given about silver? Yeah, we have two pieces of information about the silver. I've sort of run over one of them. That wasn't very good. We know that there are 11.97 milliliters. Of silver, and we know that there is 0.100 molar, and that's the information that we know about the silver. Now, are we okay with the fact that the silver is 0.1 molar because it's the same as the silver nitrate? Yes? Concentration of Ag plus equals the concentration of Ag NO3 equals that. Yes? Okay. And it says we have 11.97 milliliters of 0.1 molar. What does of mean in a mathematical sentence? Of means times. Yes? I'm going to take my 11.97 milliliters and I'm going to convert that into liters. How many liters is that? 0.01197 liters. I did not leave myself very much room there. Okay, but what we have then is we have the moles. If we want to calculate the moles of silver, we get 0.01197 liters times 0.100 moles of silver per liter, and that gives us 0.001197 moles of silver. So far, so good? Okay. What do we know about the chloride? We have, what can we say about our moles of chloride compared with our moles of silver? They are 1-to-1, so they are the same. So our moles of Cl minus are the same as our moles of Ag, which is 0.001197 moles. How do I know it's the same? Because they react in a 1-to-1 fashion. Well, okay, in a titration, what you do is you add, so you would have in your reaction flask, we've got some Cl down here. Yeah? And did you do a titration last year? No, okay. So that's why this is unfamiliar to you. Don't worry, we'll actually do like a whole thing on it. This is just a little preview for you, okay? We have a burette. Are you familiar with a burette? Yes, okay, cool. Up in here, we have silver nitrate. But I'm just gonna put silver because I don't care about the nitrate, okay? So what's gonna happen is I'm going to drip in some silver, Ag+. These two guys are gonna get together, they're gonna react, and all I'm gonna be left with now is one chloride left, right? I've got AgCl precipitate, and I still have one chloride ion left. We're really simplifying this. And then I add another drop of Ag+. Okay, and we get, these two guys get together and form a precipitate, and we get AgCl. So now we have a little pile of AgCl solid at the bottom, and we don't have any chloride ion left. Okay, now the trick is that we would need to add something to indicate that the reaction is over. Okay, so what we're going to have in here is we're going to have added a CrO4 2- ion. This is our indicator. Yes? And silver actually prefers to react with chloride over chromate. So the chromate's just going to sit in here. Okay, we would have had chromate from the beginning, CrO4, 2-, CrO4, 2-. It just hangs out until the chloride's all gone. And then the moment we add another drop of the silver, and this time I'll put 2 Ag+ just because we need 2 of them to react with the chromate, okay? We will now have, in our beaker, flask, sorry, Erlenmeyer flask, we'll have AgCl, and it won't actually be sitting at the bottom. It'll be cloudy. You'll get a cloudy white precipitate, okay? But now we're also going to have Ag2CrO4 solid, and this is a brick red precipitate. So all of a sudden, what you're going to see is you're going to see white precipitate, white precipitate, white precipitate as the silver chloride forms. The moment you run out of the silver chloride, you're going to get a brick red color forming. Okay, and that tells you all the chloride is now gone. So all the chloride has been reacted. You've added a couple extra particles of silver, but not very much. So that means that the silver and the chloride were exactly equal. And that's the point of a titration, is for those two particles in the titration to exactly fulfill the stoichiometry. If it's a 1-to-1, there will be exactly the same. If it's a 1-to-2, you'll have exactly 1 of this and 2 of that. Does that make sense? Okay, and like I said, we're going to spend a lot of time on titration, so if that didn't make any sense and you didn't do it last year, don't worry, we will get there. We're going to spend lots of time talking about titration. All right, so the moles of chloride is equal to the moles of silver, and then we would need to find the concentration of the chloride ion, so that's going to be 0.001197 moles divided by, and I'm going to give you an option here. Is it going to be 10 mils? Is it going to be 11.97 mils? Or is it going to be 21.97 mils? Have a chat about that. So we started with 10 milliliters of well water that contains some chloride. Yes, we had a chloride and we had a chloride. Yeah. And then we reacted some of that chloride and it became some silver chloride. So we still had 1 chloride left. And then we reacted it with some more silver. And then we had no chlorides left. So by the time we get to having added all of the 11.97 mils of silver nitrate, how much chloride is left? No chloride. So what is the concentration of chloride in the 21.97 combined volume of the two solutions? 0. We don't want to know the concentration of chloride after it has been reacted because there should be nothing left. Yes? We want to know what was the concentration of chloride in the well water. How much well water did we have? 10. When you are titrating, never combine volumes. Okay? When you are titrating, never combine volumes. You're always going to treat the two volumes separately, one for the silver, one for the chloride. or one for the acid, one for the base. I will repeat that many, many times. Yes? Never combine volumes in a titration. Never use M1V1 equals M2V2 in a titration, ever. It works occasionally just by happenstance, which is irritating because then people think, oh, it worked. Now it will work all the time. And then they get it wrong and they're like, I don't understand why I got it wrong. And it's because that formula is not meant to work that way. That formula is for dilutions. Okay. Do you guys remember M1V1 equals M2V2? The magic formula from last year? I was speaking to a student who graduated from here about 4 or 5 years ago. Just is going to be graduating from U of T this year. And she's applying for PhD programs. And she's been doing some research on stem cells. They are trying to get stem cells to differentiate into cardiac pacemaker cells. So in other words, rather than you know how the electrical signal in the heart for some people doesn't work properly? Okay, and they have a pacemaker in there, like a little electronic device that actually goes zzz, zzz, makes the heart beat. They're trying to get it so that if you got those stem cells in there, it would just grow into a natural pacemaker and you would never have to like get the battery replaced or whatever, or have this like weird lump on your chest. Both my parents have pacemakers right now. They're both 80 something, right? So this is really cool and interesting. And you know what she told me she uses from chemistry all the time? M1V1 equals M2V2. There's a lot of diluting in both biology and chemistry. It happens all the time. So if you know that one, you're good to go. Okay, for a lot of stuff. All right. But yeah. But never use it for a titration because it doesn't work in titrations. It's for diluting. Okay. I'm actually going to grab this one. And if you would like to grab some paper for this one, we're going to do this last one. First of all, calculate the concentration of chromate ion in a saturated solution of calcium chromate, and you are given the KSP. Is this going to be a solubility equilibrium equation, or will this be using a precipitation equation? Solubility equilibrium equation. Please write the solubility equilibrium equation for this question. Did you guys write it? Yes, good. Ca, CrO4. What state? Solid. What kind of arrow? Equilibrium arrow. Gives Ca2 plus CrO4 2 minus. Okay. Now, if you wanted to solve this question, I know we haven't done one like this, but what might be useful to write? KSP, yeah. KSP equals what would it equal? Calcium, Ca2 plus, times CrO4, 2 minus. Now, what do you know about how much of this stuff dissolves? Like if we started with just solid and we had ICE, and we can't use this because that's a solid, right? And we start with nothing dissolved because when we put it in, it's all solid. By how much would it increase? Do we know how much? By X, yes. Could we solve this equation? Goodness, yes, we could. 7.08 times 10 to the negative 4 is equal to x squared. X is equal to 7.08 times 10 to the negative 4 square root 0.0266. So the concentration of CrO4 2 minus is X is 0.0266 molar. Look at that. You know how to do like half of section 3.3, and we've not even started it yet. You've done a titration question. You've done a given a KSP, find the ion concentration. Do you guys remember what the word molar solubility meant? How much dissolves? Molar solubility. How much dissolves? Concentration. What is the concentration of CaCrO4 in this question? .0266, because this is a 1 to 1 to 1. So now that you know what molar solubility is, I could say, instead of saying calculate the concentration of the chromate ion, I could say find the solubility, the molar solubility of calcium chromate. So close to being done this unit. Just kidding, we got a little bit more to do, but there's a bunch of qualitative stuff too. This is as far as I got with the other class. In fact, I didn't even get through this last one because we spent a lot of time doing review stuff, like going over the review. They asked a lot of questions. So we are done. So if you wanted to take the next 10 minutes to say, do the homework, which was what, page 20, number 1A and 2A, you could knock that out of the park and go home and just study.